Okay, there's lots of different notation for derivatives, so I want to go over that really quickly. So the notation for the derivative of f of x equal 5x cubed, we can write this as f prime of x, or we could write it as y prime dy dx, df dx. So this is called Leibniz notation. We could also write it with a d dx and then just write the function inside of the square brackets. We don't have to stop at the first derivative. We could also find the second derivative, third derivative, fourth derivative. We just repeat the process of, using the definition. So here's the notation for the higher order derivatives. If I wanted to take the second derivative, I could write this as f double prime of x, y double prime, or I can use the Leibniz notation again. I just have the x higher order here, and here you can see the Leibniz notation, and etc. F triple prime, y triple prime. We could keep going. So here's a very important theorem, and it states that if f is differentiable at x equal a, then f is continuous at x equal a. So in other words, differentiability implies continuity. And that's an important thing to remember. The proof is in section 2.8. The way that I'm going to use this a lot is that I'm going to use the contrapositive. I'm going to say that this statement is equivalent to saying that if f is not continuous at some value a, then it's not going to be differentiable. So if you're not continuous, you can't be differentiable at that value of x. So that brings us to the next question. When does a function fail to be differentiable? Functions fail to be differentiable when they're wherever they're discontinuous. They fail to be differentiable if there's a corner, like in the absolute value function, so there's a sharp change in the tangent lines. If there's a cusp, or if there's a vertical tangent line, something that looks like this. In all of these cases, the derivative will not be defined. In your homework for section 2.8, I believe it's question number 20, you'll go through the absolute value function example and you'll see why the derivative fails to exist at x equals 0 for the absolute value function. Down here, I'm just going to do a quick example, another example where we're going to sketch the graph of f prime using the graph of f. And in this example, there are lots of places where the derivative is going to fail to exist. Here I have a corner. Okay, so I'm going to have a problem. There will not be a derivative at -2. Here I have a discontinuity, another discontinuity at 1, a cusp at 2, and discontinuity at 3, and a vertical tangent line at 4. So we're going to do a quick sketch and see what this would look like. Okay, well, it appears that the slopes of all of the tangent lines in this interval are going to be -1. Okay, so I'm going to draw that in my graph all the way over to 2. At 2, I'm going to have an open circle because the derivative function will not be defined where there's a corner. Now, as I move to the right of 2, it seems like the slopes are approximately 1. So if I were to draw the tangent lines, their slopes would be 1. So I have my circle at -2. At -1, I have a discontinuity. So I'm going to have an open circle there because the derivative is not defined at a discontinuity. But it appears here that the slope along here is 1 the whole way across. So, or the slope of the tangent lines here, sorry, is 0, because it's just a horizontal line segment. When I get over here, it appears what's happening around this cusp is that the slopes of the tangent line start off around 0, but then they get extremely steep approaching a vertical line, like a kind of vertical tangent in there. So what that looks like down here is that my tangent lines start around 0, but then they seem to get very steep in a negative slope, with negative slopes. The opposite happens over here, where the tangent lines are extremely steep near 2, to the right of 2, but they've got positive slope. So this is going to look like a asymptote, a vertical asymptote in my derivative. Again, my derivative is not defined at 3, so I have an open circle. It looks like it's about 0 to the right of this point, and near this horizontal tangent, or near the vertical tangent, the tangent lines appear to have getting increasingly steep, but in a negative direction. Over on the right-hand side, the slopes are still negative, but they're going from very steep to less steep, so maybe the tangent line starts to look like something like this and starts to approach 0 like this. So that's a rough sketch of the derivative of this very difficult function.